Thank you for coming. The title of my talk, Math, Magic, and Mystery, is actually stolen from the name of Mathematics Awareness Month for the year 2014. This year's theme is Mathematics, Magic, and Mystery, which is not coincidentally also the title of a book by Martin Gardner. And if we go to the web, you can find a wonderful web page. There's a picture of Martin Gardner at the top. And if you scroll part of the way down, you can see a calendar of the month of April. Each one of the days is a different, interesting mathematical morsel with video footage and explanatory text. So it's a wonderful way to spend the month of April, just learning all kinds of interesting new math. Martin Gardner, shown at the top there, was, I think, the greatest popularizer of mathematics of all time. He had an interest in mathematics and in magic, and many magic tricks actually have a mathematical basis, and that's certainly one of the sources of the popularity of Gardner's column, is the way he mixed math and magic together. But I want to say that the kind of magic that he was interested in is stage magic, or illusionism, or sleight of hand. It's not the real magic. And by the real magic, I mean the stuff that you believed in when you were a kid, and then you realized didn't actually exist, and then gave up on, except in as much as you can read about it in books written for children and for adults who never lost their interest in that magical, wondrous view of the world that says that underneath the reality we see, there's something deeper and strange and powerful and marvelous. And stage magic can be a substitute for real magic, but only if you don't understand what's going on. As soon as you understand how the trick is done, it becomes less interesting, less awe-inspiring. Mathematics, for me, is a kind of substitute for the real magic, but with the opposite quality. The more you understand it, the more awe-inspiring it is. So I'm going to talk about the ways in which mathematics is, for me, like the real magic. But in order to do that, I have to detour a bit and talk about what modern pure mathematics is like. Math is an old subject, but it underwent two important transformations in the last 200 years, in method and in matter. In method, there was a new standard of rigor introduced a couple of centuries ago in the desire to make calculus a more rigorous subject and to replace intuitive notions of limits that had dissatisfied some people by something completely cut and dried and unambiguous. With these new standards in rigor, intuition was not displaced, but it came to fill a new role that was separate from the role played by rigor. The two of them worked together in tandem, kind of like a driver of a vehicle and a navigator of the vehicle, working very closely together to make progress. And I think a large part of this revolution came from Bernard Bolzano, a priest and mathematician, who in the early 1800s proposed a new notion of the limit concept, which undergraduates here have probably encountered, the so-called epsilon delta definition of limits. For every epsilon bigger than 0, there exists delta bigger than 0, blah, blah, blah. You'll get to see some of that blah, blah, blah on another slide. But the point I want to make is that this is a difficult transition for many undergraduates to make. And yet, once you get the hang of this kind of way of thinking with epsilons and deltas, suddenly the whole world of post-high school mathematics and postgraduate mathematics is open to you. Let me give you a quote from mathematician Paul Halmas. "The day when the light dawned, I suddenly understood epsilons and limits. It was all clear. It was all beautiful. It was all exciting. It all clicked and fell into place. I still had everything in the world to learn, but nothing was going to stop me from learning it. I just knew I could. I had become a mathematician." I also mentioned that the matter of mathematics changed. Before, it had been about numbers in the sense that the common understanding went, and space, the kind that you see in front of you, or two-dimensional space. But suddenly there was an explosion of what math could be about, made possible in part by the new, more rigorous approach, which allowed you to go beyond what your intuition could grasp by making formal definitions of objects and letting the intuitions come later. So for example, we have higher dimensional Euclidean geometries, not just 2- and 3-dimensional, but 4, 5, and 6. If you can write down what their properties are rigorously, you can prove theorems about them, even if you can't picture them. Going beyond even higher dimensional Euclidean geometries, we have non-Euclidean geometries. such as, well, here's a picture illustrating the range of possibilities you can get. A famous postulate from Euclidean geometry is that if you have a line L and a point P not on that line, there is one and only one line you can draw through the point P that will not intersect the line L. Mathematicians tried to prove this postulate from Euclid's other postulates and failed to do so, and then eventually realized the reason they couldn't prove it is because there were other geometries that are possible. There are geometries in which there are no such lines through the point P at all, so-called elliptical geometries, and then geometries in which there are infinitely many lines that you can draw through the point P that do not intersect the line L, so-called hyperbolic geometries. And all of these geometries are consistent with the other axioms of Euclid. And so now we no longer have a single geometrical universe, but a whole multiverse of different possibilities sitting side by side. Going beyond that, we have strange number systems. Going beyond the familiar real numbers, including the complex numbers, but also stranger numbers, like the p-adic number system. So if you think that the series 1 plus 2 plus 4 plus 8 plus 16 plus ... converges, you are right if you happen to be thinking in the 2-adic mathematical number system. So mathematics expanded enormously in terms of what it could consider. And the end result is that math was liberated from reality, or rather, liberated from merely physical reality. It did not become a mere fantasy because everything that is rigorously defined has a rigorous answer, even if the answer is you can't decide. And so now we suddenly have a much broader range of things to think about beyond what we can merely imagine. Tools of the mind that were created to help us understand this world have been repurposed as tools for transcending it. Here's a quote from J.J. Thomson, the physicist. In fact, the pure mathematician may create universes just by writing down an equation. And indeed, if he is an individualist, he can have a universe of his own. So my sources of information on magic are going to be these 3 books. How many of you have read the book Half Magic by Edward Eger? Okay. Okay. So that was a big influence on me. More recently, The Magicians by Lev Grossman. Anyone read that? Okay. And I'm going to guess perhaps you've also read The Name of the Wind. Okay. 3 for 3 here. Let's go to the next slide. Here's a great quote from Half Magic. The trouble with life is that not enough impossible things happen for us to believe in. But mathematics is full of impossible things to believe in. The first clue that I had that the book The Magicians by Lev Grossman, written in the past decade, was going to have a lot to say to me about my experience as a mathematician was this description of the entrance exam at the Brakebill School for Magic, an elite school for young magicians, college-level institution, somewhat analogous to Hogwarts, but different in very interesting ways. The admissions test is a math test. A lot of the test was calculus, pretty basic stuff for Quentin. Quentin's other homework, this is a later passage after he's been admitted, turned out to be a thin, large format volume containing a series of hideously complex finger and voice exercises arranged in order of increasing difficulty and painfulness. Much of spellcasting, Quentin gathered, consisted of very precise hand gestures accompanied by incantations to be spoken or chanted or whispered or yelled or sung. Any slight error in the movement or in the incantation would weaken or negate or pervert the spell. So here's a typical sort of thing we see in math. Again, the slightest error will negate or pervert the content of it. This is a definition, and this is the kind of thing we expect our undergrads to learn how to work with. The limit of f of x as x approaches a equals L if and only if, for every epsilon bigger than 0, there exists a delta bigger than 0 such that every real number satisfying 0 is less than the absolute value of x minus a is less than delta satisfies absolute value of f of x minus L is less than epsilon. And I want to point out here a point of resemblance with magic, namely the use of symbols from an ancient language, in this case, Greek. And here's a typical sort of finger exercise we ask our students to do. And they may make errors that they think are minor, and we say, no, no, that's wrong. You can't do it that way. The problem is to show that the limit of 2x as x approaches a is 2a. And the proof we ask students to give is something very close to the following. Given epsilon bigger than 0, let delta equal epsilon over 2. Then for every x satisfying 0 is less than the absolute value of x minus a is less than delta, we have absolute value of 2x minus 2a is equal to twice the absolute value of x minus a, which is less than 2 delta, which equals epsilon. So absolute value of 2x minus 2a is less than epsilon as claimed. And here again I want to point out the resemblance to magic. A certain mathematical quantity, epsilon over 2, is being summoned like a spirit from some other realm. And we are binding it to a symbol, to delta, and capturing it and bringing it into the scene. And also note the use of the word let. There's a kind of a magisterial quality to what the mathematician does when they say, let this variable equal that. And I think it's a power students are often slow to claim for themselves. They don't realize it's not just professors who can let. Students can let too. And once you realize you can say, let P be the midpoint of this line segment, you can just do that. And often that's the key to solving a problem. Another feature in common between magic and math is this idea that there are separate worlds from each other within math. In Narnia, or rather in the world of C.S. Lewis, there are these parallel worlds of Earth, Narnia, Charn, and so forth. It's hard to get between them. And in Lev Grossman's universe, there's Earth and Fillory and other worlds. And in math, there are all these specialties, geometry, statistics, number theory, and so on. And they're very different disciplines with very different terminologies, very different concepts, very different algorithms. Experts in one system may find themselves at a loss when confronted with work done in another field. But there are also bridges between worlds. In C.S. Lewis, it's the wood between the worlds. In Lev Grossman, it's the Netherlands. And in math, it's some mysterious glue that holds math together and keeps it from splitting into unrelated specialties. And perhaps I'll say a little bit more about that mysterious glue later on. But let me tell a tale from Eugene Wigner that talks about this glue a little bit. This is from his essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. There is a story about two friends who were classmates in high school talking about their jobs. One of them became a statistician and was working on population trends. He showed a reprint to his former classmate. The reprint started, as usual, with a Gaussian distribution, and the statistician explained to his former classmate the meaning of the symbols for the actual population, for the average population, and so on. His classmate was a bit incredulous and was not quite sure whether the statistician was pulling his leg. "How can you know that?" was his query. "And what is this symbol here?" "Oh," said the statistician, "this is pi." "What is that?" "The ratio of the circumference of the circle to its diameter." "Oh, well, now you are pushing your joke too far," said the classmate. "Surely the population has nothing to do with the circumference of the circle." And yet, of course, it does. And pi also turns up in number theory, even though that seems fairly far removed from the geometrical context in which pi originates. So now I want to enter into the heart of my talk, which is what is magic good for? And in what ways does research in mathematics satisfy some of those needs for me, and I suspect other practitioners as well? So let's run down this list. Wealth, love, being invisible, power, being able to fly, eternal life, or at least very long life, traveling through time, traveling to other worlds, transforming yourself or transforming things in the world around you, or making something from nothing. And number 10, I wrote harmony. I mean, world peace is sort of what I had in mind. I don't think I want to keep it that specific, but I will say reconciliation or harmony. So let's start with wealth, okay? So I don't have much to say about wealth, except I will say that kind of begs the question from the point of view of what you want magic for. Because wealth in and of itself doesn't get you anything. It's what you spend the wealth on. And so the question is, what would you use the money for that you couldn't just use magic for better if you had access to magic? Number 2, love. Yeah, I don't think anyone goes into mathematics to win anybody's love. So we have 2 that didn't work out, but let's go on to the next few, and I think we'll see some more interesting things. Invisibility. Well, there is in fact some work on what's called cloaking in applied mathematics, which is the idea that you could create a device that would bend light around an object or other forms of radiation so it would be effectively invisible, at least from certain angles, ideally from every angle. It's a subject of active research in applied mathematics. It's not an area that I know much about, So I'm not going to say anything about it. And also, I'm more interested in talking about the multiverse of pure math today, although applied math is extremely important and beautiful. What about power? Well, power is about a disparity between effort and effect. I was going to originally show you a clip from Fantasia showing Mickey Mouse waving his fingers back and forth while a broom carries buckets of water and does all the work. That's what a sorcerer wants to be able to do. Well, what could be a better form of sorcery than exerting a finite amount of effort and achieving an infinite amount of work? Well, I want to point out a way in which math does this for you. Here's a proposition. For every positive integer n, 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 over 2. That is, 1 is equal to 1 times 2 over 2. 1 plus 2 is equal to 2 times 3 over 2. 1 plus 2 plus 3 is equal to 3 times 4 over 2, and so on. So understood this way, there are infinitely many things you have to prove. So you could say, wow, how could I ever hope to prove that general formula when it has infinitely many cases I would have to settle? Well, in fact, mathematicians have a magic wand for proving all infinitely many propositions in this family at once. It's proof by mathematical induction. If you can prove that the first assertion in that list is true, and that the truth of any particular assertion in that list implies the truth of the next assertion on that list, then they must all be true. An analogy I use when teaching this to undergraduates is imagine lining up a row of dominoes close enough together so that when the first one falls, it'll topple the second one. And they're all spaced equally far apart, so the second will also topple the third will topple the fourth, and so on. They'll all fall down. And that's what proof by induction is. Except, who set up the dominoes? Nobody had to set them up. If they had, we'd be in trouble because there are infinitely many of them. They sort of come set up in that way. And I'll come back to that mystery later. The other mystery is, in some sense, we are proving infinitely many assertions, and so we are mastering or handling infinity, but our minds are finite. So how can we do that? So I think this captures some of the sense that a magician is someone who is on intimate terms with infinity, and in that sense I feel also that pure mathematics has this magical aspect to it. What about flight? Well, let me show you here. This is a flyover of a three-dimensional surface related to the Mandelbrot set. Right now we're not zooming in, but shortly the camera is going to zoom in closer, and we'll be getting closer to this set. It may remind you of a movie called Powers of 10, but Powers of 10 was limited by the fact that there's a larger scale beyond which you can't go, the size of the universe, and there's a smaller scale beyond which you can't go, the Planck scale. But in mathematics, there are no limits to how much you can zoom in. So the Mandelbrot set has structure at every level, and you could create a flyover that would let you go in much deeper than you can go into the physical universe with zooming in. And I'm hoping that someday there will be a video game that lets you fly over the Mandelbrot set and zoom in and do various maneuvers. The opposite of flying is burrowing, which can be magical too. And I want to quote from Galileo here. The book of nature is written in the language of mathematics. So in some sense, mathematics is under everything else. It's even underneath physics, because we can imagine the laws of physics being different, but it's very hard for us to imagine the laws of mathematics being different. Life. Sometimes one might think one would want to live forever, but when you stop and think about that, that's almost even scarier than dying. So I don't think I would want to live forever. I think ideally I'd like to live for 5 or 6 generations, enough so that I lose track of my offspring. Well, in the world of math research, we get to do this because the cycle of procreation is much shorter. By procreation, I'm not speaking in the literal sense. I mean the sense in which a person in a certain field reproduces themselves with someone kind of like them. And so a young PhD could have grad students, less than 10 years out of grad school, who would then have grad students 10 years later, who would then have grad students later. So if you're an active mathematician for 70 or 80 years, you could have great-great-great-grand students whom you collaborate with. In each generation, you try to reproduce your tastes, your enthusiasms, your outlook. Students will have some of their own creative ideas to add to what you give them, and you'll get to see those ideas change and morph over time, the same way what you give to your children changes and morphs over time as they pass it to their children, and so on. So for me, one of the satisfactions of being in math is getting to see this generational turnover, but at an accelerated pace that effectively gives me more of a lifespan as measured in cycles of regeneration. Time travel. Can we travel back in time? Well, let me show you a bogus proof of that same proposition I showed you before. Show the limit of 2x as x approaches a is 2a. Proof, given epsilon bigger than 0, let delta equal, oh, I don't know what to let delta equal. Well, let's let delta equal epsilon. Then for every x satisfying 0 is less than the absolute value of x minus a is less than delta, we have absolute value of 2x minus 2a equals twice the absolute value of x minus a, which is less than 2 epsilon. So the absolute value of 2x minus 2a is less than 2 epsilon. So, and now I'm stuck, because I was supposed to show that the absolute value of 2x minus 2a was less than epsilon, but I showed that it was less than 2 epsilon, which is not quite what I needed. What do I do? Well, now that we see what went wrong, we can go back in time and fix it. Go back to the place where we made a mistake, namely letting delta equals epsilon, and change it to something else. So here I want to go to this DVD. This is from Bill and Ted's Excellent Adventure.
Our historical figures are all locked up, and my dad won't let them out. Can we get your dad's keys? Couldn't steal them, but he lost them 2 days ago. Only we could go back in time to when he had them and steal them then. Well, why can't we? We don't got time. We could do it after the report. Ted, good thinking, dude. After the report, we'll time travel back to 2 days ago, steal your dad's keys, and leave them here. Where? I don't know. How about behind that sign? That way, when we get here now, they'll be waiting for us. See? Whoa, yeah! So, after the report, we can't forget to do this, otherwise it won't happen. But it did happen!
Okay, so that's something you get to do in mathematics. Let's talk about other worlds. Well, I've sort of mentioned some of those other worlds before. These strange geometries and strange number systems and other strange things one encounters in mathematics. What about transformation, alchemy? Well, here's an example of mathematical alchemy. It's a problem that was considered by Slater, Tarjan, and Thurston in computer science, which they solved using three-dimensional hyperbolic geometry through a series of transmutations of the problem. First, they started with objects called trees, which are data structures. They turned it into a problem in plane geometry, where we've got polygons that are triangulated by diagonals in various ways. Then they turned that into a problem in solid geometry. And finally, they passed from Euclidean to hyperbolic geometry to move the problem to a setting in which volume turned out to be a useful measurement of distance. And then they could get useful estimates for the original problem. But the kind of math that I most enjoy is math that has this dynamical, transformative quality of taking a problem and changing the flavor of it by moving it within mathematics from one perspective and one branch to another, gaining new insight and new techniques as one goes. Here's another example. This is the example of everting a sphere, turning a sphere inside out.
Hey, I read somewhere that mathematicians can turn a sphere inside out.
Yes, that's true.
What's the big deal? Just poke a hole in it and pull it through.
Sure, but the point is to do it without making a hole.
But then it seems impossible.
You're right. You cannot do it with an ordinary sphere, like a basketball. You have to understand the rules of the game. This sphere is made of an abstract elastic material that can stretch and bend and pass through itself. But you cannot rip or puncture this material without destroying it, and you cannot crease it or bend it sharply.
If the surface can pass through itself, what's the problem?
Do you think allowing self-intersections makes it easy? Try it.
I'll push the two halves right through each other.
Be careful. What about that ring around the equator? Remember, you mustn't tear or crease it.
Let me try again.
That's no good either. You're pinching it infinitely tight.
But then there's no way. It's impossible. You'd have to crease or pinch it to turn it inside out.
It is surprising, but watch this.
Is this it? Is this a sphere turning inside out?
You bet. That wasn't easy to follow, was it?
So this is an example of one of the strange things you can do in mathematics. It's extremely unintuitive. And I have to say, I still do not understand it. But I'm hoping someday that somebody builds a virtual reality interface that will allow me to manipulate this kind of surface with tactile feedback, so that even though my hands aren't touching anything, I've got some sort of gloves and some sort of goggles that let me feel like I'm interacting with a surface that can pass through itself in this way. And I think
Google Gloves.
Yeah. So I think your generation is going to probably invent things like this, probably for other purposes of gaming, but an incidental spin-off will be being able to turn a sphere inside out. So, another example I want to show you is the Banach-Tarski paradox. Okay, let me stop that quickly. Thank you. So there's three colors of region here, but you should focus your attention on the orange region. The three regions are congruent to each other if you rotate them by a third of a circle. And so they all would seem to be 1/3 of the full region. And in particular, the orange region is 1/3 of the whole region. But this is not to be viewed as a subset of the circle in Euclidean space. It's to be understood as the entire hyperbolic plane. And so this motion that we're seeing there is actually one of the symmetries of the hyperbolic plane. And now if you rotate this picture about its center, you can see that this orange region has now become half of the hyperbolic plane rather than 1/3. So somehow by sliding this set, we have changed it from being 1/3 of the hyperbolic plane to 1/2 of the hyperbolic plane, basically creating 1/6 of the hyperbolic plane out of nothing. Let's talk finally about harmony. So life is full of disagreements, and there are some ways to resolve disagreements that sort of evade the idea of one person being right or one person wrong by saying, well, you're right and you're right too, for everything is basically one thing. There are no distinctions or differences between anything and anything else. Or by a form of disengagement that says, well, let's agree that we disagree. But the mathematical multiverse offers something more interesting. It's a kind of rigorous relativism. So Euclidean and non-Euclidean geometries could be seen as being mutually contradictory because they assert different things about points and lines and their properties. However, every non-Euclidean space can be embedded in a Euclidean space of higher dimension and vice versa, as long as you appropriately adjust what you mean by words like line and point. So that rather than being mutually contradictory, the different geometries are mutually supporting. So here's an example of how this is done with a patch of two-dimensional hyperbolic space being embedded in three-dimensional Euclidean space, something called Gabriel's horn. And what we mean by a line in hyperbolic space is now a curve that must travel on the surface of Gabriel's horn, but be as short as possible, subject to that constraint. And so in this way, we sort of bring together all the different geometries into a unified whole, where each of them can be seen as being a part of all the others in high enough dimensions. For the final part of my talk, I'll get into the theme of mystery and point out various mysteries within the subject of mathematics and its relation to reality. I've already referred to the unreasonable effectiveness of applied mathematics. And this is a subject that many people have thought about. But I want to say that from a certain point of view, it might not be so surprising. that mathematics turns out to be so useful. Because after all, the universe is responsible for the ways our brains work, and our brains condition the kinds of math that we have. So perhaps it's not so surprising that our math can then feed back in useful ways upon understanding the universe. I think a deeper mystery, at least deeper for me, is the unreasonable relevance of pure mathematics. For example, complex numbers were invented in the Renaissance with no practical purpose in mind, and yet they turn out to be very well suited to describing electromagnetism. Why should that be? Here's a quote from Giancarlo Rota. "Of all escapes from reality, mathematics is the most successful ever. It is a fantasy that becomes all the more addictive because it works back to improve the same reality that we are trying to evade." The unreasonable tractability of mathematics. I said before, who arranged those dominoes? Or rather, why are they so close together if nobody put them that way with our wishes and needs in mind? I think the biggest mystery for me, though, is the unreasonable interestingness of mathematics. How can we possibly be surprised by what we find when we do mathematics, when mathematics is just the spinning out of consequences of rules that we ourselves have chosen? Here's a quote from The Name of the Wind. This is a young magician's experiences in being trained in the art of magic. "He also taught me a game called Seek the Stone. The point of the game was to have one part of your mind hide an imaginary stone in an imaginary room. Then you had another separate part of your mind try to find it." Now, my mind doesn't work this way, and I doubt anyone's mind really works this way unless you're insane. But in a sense, math is like that. Math gives us all these theorems, which in some sense you might say we latently knew because we chose the rules, and yet we're very surprised to find out what it leads to. So why should math appear to give us back more than we put into it? Why is math so interesting to us? Well, it's possible that this last mystery is just a temporary state of affairs caused by our incomplete evolution. Maybe human math is interesting to humans because our brains are broken. And maybe as we as a species get better at math, we'll find it less and less interesting. But we're nowhere near that point yet. For the past 100 years, mathematical history has always been at the exact point where C.S. Lewis took his leave of Narnia. All their life in this world and all their adventures in Narnia had only been the cover and the title page. Now at last they were beginning chapter 1 of the great story, which no one on earth has read, which goes on forever, in which every chapter is better than the one before. And so I will leave you with the victorious cry of the Narnians as they move on from their last battle into the glorious future. Further up and further in. I hope some of you will join the adventure. Thank you for listening.
I was just going to have a comment. You mentioned that there wasn't any good examples of people seeking mathematics for love or whatever.
Mm-hmm.
There's a great movie called IQ, which a guy actually seeks Meg Ryan out and tries to learn mathematics because she's a mathematician. So
Oh.
You got an example.
So I'll have to view the movie IQ to see if...
It's okay.
Okay.
Where do you think something like the proof that the square root of 2 is irrational or something, the Pythagoreans had this whole sense of mysticism bound up with their mathematics, and epsilon deltas feels like a very modern kind of thing that we've constructed to try and make sense of things, but then these much older things, do they have a place in your ontology?
The older things. Well, there was that pentagram in that tarot card for the magician, which makes me think of the irrationality not of the square root of 2, but of the golden ratio, which is a sort of ancient result. And one of the proofs that the Greeks might have had for this result was a proof by contradiction, where you try and find an integer pentagram, and you find out that it must have a smaller integer-sided pentagram inside it, and must then have an even smaller integer-sided pentagram inside that, leading to an infinite regress of smaller and smaller integers, which we know we can't have because any descending chain of integers has to stop. It can't go on forever. So that's a proof by contradiction. I guess for me, proof by contradiction connects to flight by way of a joke of Douglas Adams, who said that the way you fly is you throw yourself at the ground and miss. And proof by contradiction is basically throwing yourself at the ground and missing. You try and find a counterexample, and by missing the counterexample and getting into trouble when you try and construct it, you construct a proof. The cool thing about math is that in math, not only can you fly by throwing yourself at the ground and miss, you can do the reverse as well. You can, well, I don't know how to turn it around exactly, but the way you can find a proof is sometimes by trying to find a counterexample and missing, but sometimes the way you find a counterexample is by trying to construct a proof and missing. So it kind of works both ways. So I don't know if that quite answers your question.
No, and it's interesting how you've got the in those nested golden ratios, pentagrams that you were talking about, is also the idea of proof by induction kind of lurking in there too.
That's right, induction and infinite descent, and yeah, that's right. Other questions?
Let's thank our speaker again for a lively and talk. Thanks to all of you, prize winners, and everybody who's here to support them.
Do you have any last mathematical words, Jim?
Yes, I do. Algebradabra.